Hi everybody, and welcome to example 2 on page 45 of the workbook. And in this example, we're going to be talking about a problem that we've already looked at actually, the idea of finding the equation of a tangent plane, but from a little bit different of a perspective. Okay, so they'd like us to find the tangent plane to the surface that looks like this at a particular point. And I want to start by reminding you that we already have a way of doing this in a particular situation. So for a surface that's written in the form z equals f of xy, we have a formula for finding the equation of a tangent plane. It involved finding partial derivatives. But the issue that we run into here is that our formula is not in that form. Notice that the z occurs actually in several different places in our formula, and so it's probably not even possible to write this formula in the form z equals f of xy. And so to do this, to find this tangent plane, we need a genuinely new method here. Okay, and the nice thing is we can use gradients to help us with this process. All right, so how could we approach this? Well, let's start with kind of a key observation here. If you want to find the equation of a plane, a very helpful piece of information is a normal vector. Okay, if we can find a normal vector to the plane, we already know a point, and so that would be enough information to find the equation. All right, how do we do that? Well, let's start with the equation we're given. Okay, 2e to the z equals cosine of z plus x cubed yz plus xy cubed. Okay, I'm going to take that and just rearrange that equation by getting everything on one side. So let's subtract 2e to the z over to the right-hand side so that we have a 0 on one side of the equation. Okay, so this is going to look like cosine z minus 2e to the z plus x cubed yz plus xy cubed equals 0. And notice that all we did was just took this 2e to the z term and subtracted it to the other side. That's the same equation. Okay, and then what we're going to do is to give this expression that we have here a name. We're going to call it f of xy, capital F of xyz. Okay, where capital fxyz is just the expression that I circled. Cosine z minus 2e to the z plus x cubed yz plus xy cubed. Okay, now what's significant about that? Well, by doing that, notice that what we're really looking at here, okay, if you kind of look at this equation as a whole right here, I'm going to see if I can sneak this in. This is a level surface of this function capital F that we just created. Why is it a level surface? Well, we took the function capital F and we set it equal to a constant. That's exactly the definition of a level surface. Okay, and the reason that that's helpful is we know that gradient vectors are orthogonal to level surfaces. So by identifying this surface that we started with as a level surface, it gives us a way to find a normal vector by calculating a gradient. Okay, so let's put that into words first. Okay, since our given surface is a level surface, gradient vectors will be normal to that surface. Okay, that's the key fact. That's kind of where this solution is leading that we're writing here. All right, so let's calculate the gradient. Okay, and again, that involves taking a bunch of partial derivatives. Okay, and all of this is referring to this function. So we're gonna take that function and take its derivatives with respect to x, y, and z. Let's start with x. So the derivative with respect to x First two terms are going to go away because they've just got z's in them. And then we're going to get, let's see, a 3x squared yz and plus derivative of x is 1, so we'll get a y cubed. Okay, so there's our I component. And then we're ready to take the derivative with respect to y. And again, we're going to get 0 for those first two terms. And let's see, derivative of the third term with respect to y is just going to be x cubed z, it looks like. And the last one would be 3xy squared. Okay, and then what about the derivative with respect to z? Well, there, derivative of cosine of z is negative sine of z minus 2e to the z. And then we're going to get a derivative of x cubed y, it looks like. Okay, for that last one. Okay, and so this gradient vector that we calculated is a way of getting vectors normal to this surface. We're interested in finding a normal vector at a specific point, this 1, 1, 0 that's sitting up at the top of the page. So our normal vector will be the gradient vector evaluated at 1, 1, 0. Okay, so we're going to take 1, 1, 0 and substitute it into this big long gradient formula that we just found. The nice thing is that the z value is 0, so some of those terms are going to go away. And if you substitute x equals 1 and y equals 1 into that big long formula, here's what you're going to get. Okay, you can double check my arithmetic. I plus 3j minus k. Okay, and again, we got that just by going up here and substituting in x equals 1, y equals 1, and z equals 0. Okay, and this is going to be the normal vector to the plane that we're looking for. What's the other piece of information that we need to find the equation of a plane? Well, it's a point. And notice that we were given the point directly way up at the top here, 1, 1, 0. Okay, and so we're ready to write down the equation of our plane. It's going to look like a, and remember, a is just the coefficient of the first, or it's the first component of our gradient vector, our normal vector. So we're going to get 1 times x minus 1, okay, plus 3, our next one, times y minus 1, okay, plus negative 1 times z minus 0. Okay, that we're just going back to the general form for the equation of a plane given a normal vector and a point. Okay, and that would be an okay final answer. We could maybe simplify it a little bit. So x minus 1 plus 3y minus 1 minus z equals 0. Okay, and so that's the answer to our problem. And what we've described here is a very powerful technique for finding an equation plane. And so I'd like to kind of summarize this process, what we did here. You can always use this method to find the equation of a tangent plane. Okay, so if you kind of boil it down to just a few words here, to find a normal vector, okay, to any surface given as a formula. If you look back at what we did, first thing we did is we took all of our terms and moved it to one side of the equation so that we've got a 0 on the other side. Okay, so move all terms. To one side of the equation so that your new formula has the form f of x, y, z equals 0. You might remember that from the solution that we just wrote. Okay, the f of x, y equals 0 is sitting right up there. Okay, and then after you do that, because that's written in the form of a level surface, you can just take the gradient to find your normal vector. Okay, and this technique can always be used, even if your formula is really complicated, in order to find a normal vector.